Towards the end, I introduced another concept, that is of a complete family of distributions and a complete statistic. We showed that family of distributions such as a Poisson distribution family, binomial distribution family where P is unknown, etc., they are actually complete families. Normal distribution, uniform distribution. So normal distribution with one parameter I have given with mu. Then I also gave as an exercise with another parameter where you have sigma square as a parameter. So did anybody attempt the second problem which I gave for the normal distribution, that is x1, x2, xn following normal 0 sigma square? So let me consider say one observation, because for the sake of proof actually one is enough and then later on you can change it. So suppose I consider here x following normal 0 sigma square. So if you have to check the completeness of this, so anybody has done it? Has any student solved that? Yes, let me ask some students. Rushil, have you solved this?
No, sir.
Okay, Vijay Kumar.
No, sir.
I mean, I think you have to attempt to see these problems. If you don't solve, then in the exam you will be completely unprepared, because it is not that whatever problems I have solved in the class, the same thing will be asked in the exam. In the exam, we will modify the problem. So I think you need to solve some of these. Otherwise, is there anybody who has attempted this to prove the completeness? Okay, so let me start. Let us consider, say, expectation of gx is equal to 0 for all sigma square. Okay. This distribution is 1 by root 2 pi e to the power minus x square by 2 sigma square minus infinity to infinity dx. So I can actually remove this one. This is of not much use, because this you can cancel out on both the sides. So this is but becoming nothing but the bivariate Laplace transform, and I am saying it is equal to 0 at all the points. So the function itself must be 0 due to the uniqueness of the Laplace transform. Okay, so so function gx is equal to 0 for all x. So this gives that probability of gx is equal to 0 is 1 for all sigma square. So the family of distributions normal 0 sigma square is a complete family. Now let us come to the complete statistic in these problems. For example, let me take this normal distribution problem. Normal mu1, normal 0 sigma square, etc. So which statistic we will be interested that it is complete. Okay, so generally you have already seen the identification of the statistics in each problem because you have done the maximum likelihood estimation. What is the term which is coming in the d by d theta of log of fx theta? So in all of these things you have seen certain statistic appearing. Later on we showed that such statistics are sufficient and in fact they are minimal sufficient. So we would be interested to check whether those statistics are complete. Okay, so in these problems we would like to see that. So let me see here. So suppose I have a random sample from the Poisson distribution. We actually showed that the Poisson family of distributions is complete. So if I consider sigma xi, then that follows Poisson n lambda. So if for lambda positive Poisson lambda family is complete, then Poisson n lambda is a member of the same class. Okay, so T, the family of distributions of P n lambda is also complete. So T is complete. Okay, is this point clear?
Can you repeat this?
We proved that the family of Poisson distributions is complete. Okay. In fact, I showed that Poisson lambda, that expectation of gx is equal to 0, then consequently gx is equal to 0 for all x, that is x equal to 0, 1, 2. So probability of gx equal to 0 was 1.
Yes,
now if I am considering T as the sufficient statistic here, and I am looking at the distribution of that we know it is Poisson n lambda. Now then this is in the same family because it is only multiplied by n. For lambda positive, n lambda is also positive. So this is some positive parameter, that's all. So this family is complete. So what is the definition of a complete statistic? That the family of distribution of the statistic must be complete. So here it remains. So T is a complete statistic. Is that okay?
Okay, sir.
Similarly, suppose I am considering a random sample from Bernoulli here. We have proved this binomial NP is complete if n is known and p is between 0 to 1. So here T is equal to sigma xi, I is equal to 1 to n. This will be binomial NP. Here n is known. So this is complete. So actually this combination of sufficiency and completeness, it will lead to some nice things which I will be just coming to this after explaining these concepts. So similarly, let us consider say x1, x2, xn following normal mu1, where mu is any real number. We have actually proved that this family of distributions is complete. Now if I look at the statistics, say T is equal to sigma xi, then that follows normal n mu n. If I consider say T star, that is equal to x bar, that is normal mu 1 by n. So it is of the same form. Okay. So these are all complete, like T is complete, T star is complete. Any function of complete statistic will also be complete by the definition itself. Just now I proved this one, that this family is complete. Let us look at a statistic which will appear naturally, that is, sufficient statistics, that is sigma xi square. So in this case, we know that T by sigma square follows chi-square distribution on n degrees of freedom. So actually, you can write down the distribution of this Fw is 1 by 2 to the power n by 2 gamma n by 2 e to the power minus w by t, w to the power n by 2 minus 1. So from here, I can write down the distribution of T. What is the distribution of T? See, this T is sigma square w, so dt is sigma square dw. So this will become 1 by 2 to the power n by 2 gamma n by 2 e to the power minus t by 2 sigma square t by sigma square to the power n by 2 minus 1 by sigma square. Okay. So I can simplify this. It is 1 by 2 sigma, well, 2 to the power n by 2 I can write as such, 2 to the power n by 2, then you have gamma n by 2, and then you get sigma square to the power actually n by 2. So sigma to the power n, basically it will become e to the power minus t by 2 sigma square t to the power n by 2 minus 1. So if I want to prove that T is complete, I should actually apply the definition here. Let us take expectation of GT is equal to 0. Okay. Now you write this expression integral GT 1 by 2 to the power n by 2 gamma n by 2 sigma square to the power n by 2 e to the power minus t by 2 sigma square Okay, so since this integral is 0 for all sigma square, all these terms are constant. I can forget about that. I can write it like this: g star t e to the power minus t by 2 sigma square dt 0 to infinity. Where this g star t is nothing but gt into e to the power, into t to the power n by 2 minus 1. Okay. Okay, so again, if you look at this one, it is actually Laplace transform here of the function g star t. And again, I am saying that it is equal to 0 for all sigma square. So therefore, the function should be identically 0. That means this function should be 0, which means gt must be 0. So that means probability that gt is equal to 0 is equal to 1. So t is equal to sigma xi square is a complete statistic here. Then I considered uniform distribution. Uniform 0 theta. Actually, I proved that the uniform family of distributions is also complete. Now, which statistic here I will consider? If you remember the sufficient statistics, it was the maximum of all the observations. Okay. And actually, we have written the distribution of t also. The probability density function of t is n t to the power n minus 1 by theta to the power n. So if I want to consider completeness, I should consider expectation of gt is equal to 0 for all theta, which is reducing to the condition that gt into n t to the power n minus 1 by theta to the power n dt 0 to theta, that is equal to 0 for all theta positive. Once again, this part I can remove. I can write g star t dt integral from 0 to theta is 0 for all theta positive. Okay, where g star t is nothing but gt into t to the power n minus 1. So if over every interval 0 to theta the integral of g star t is 0, that means the function itself must be 0. Which means that gt must be 0. That means probability that gt is equal to 0 is 1 for all theta. So here t is equal to xn. This is complete here. However, the picture need not be always very good. Like here, in many cases, I am able to show that the sufficient, basically the minimal sufficient statistics is complete. But it need not be always true. So you remember the exercise which I considered in one of the previous classes, probably in the last class, when I considered two normal distributions. So x1, x2, xm follows normal mu sigma 1 square, y1, y2, yn follows normal mu sigma 2 square. The mean was common. I mentioned to you that it is one of the important problems in statistical inference, this type of model. Do you remember what was the minimal sufficient statistics for this problem?
So sigma xi, sigma yj, sigma xi square, sigma yj square.
Okay, so this is minimal sufficient. So if I consider, say, a function here, say, let me call it t statistic, and one statistic I consider here to be sigma xi by m minus sigma yj by n. Okay, that is basically x bar minus y bar. What is expectation of gt in this problem? What will be expectation of gt if I take gt to be this function? Yeah, what is expectation of gt?
Zero.
It is 0 because expectation of x bar, expectation of y bar both is mu. So this is 0. But what can you say about this function gt? Is this function 0?
No, sir.
No, sir.
No,
Because
sir.
x bar is from one sample, y bar is from another sample. So you cannot say that they are 0. I mean, they are equal, isn't it? However, probability that x bar minus y bar is 0, that is actually this probability will be 0 because this is continuous random variables. So probability of equality to a point, it will be 0. So here t is not complete. So here we have an example of a minimal sufficient statistics which is not complete.
Can you directly say that it is 0, or there can be some probability, like is if some dependency is there between the samples?
In this case, I have taken independent samples as I gave in the last class. Here they are taken to be the independent samples. If it is not independent, then you have to write the joint distribution of xi's, yi's. So of course you can have this bivariate normal setup. Anyway, that will create little bit more complicated derivation. So I am not doing it right now, but you can do that problem also. Okay. So right now I'm not doing that. I will just skip that part. We'll take up another example. So let me take, say, this one. Suppose I consider x1, x2, xn following Poisson lambda, and I consider t as x bar and s square. So can you check whether it is complete? Is t complete? In this problem, we have seen sigma xi is complete. Now I am writing x bar and s square both. So is this complete? From the properties of the distribution, we already have some information. So you should be able to answer this question. I want to check whether T is complete. Yeah, so let me hear the answer from some of you. Venkat Sai.
Correct. I'm trying, sir.
Okay. Yeah, think over it. Yeah, so anybody is coming up with the solution?
Sir, T bar
Yeah.
must be, sir, T bar must be a sufficient, like minimal sufficient.
Minimal sufficient in this problem, you know, it is sigma xi or x bar. So
Yes.
this is little more than minimal sufficient, but it is sufficient definitely.
Yes, sir.
Yeah, it is something more. Yeah.
Then we claim about completeness, because
Yeah, so you have to answer whether it is complete or not. I mean, I have added something more. I mean, it remains sufficient because in the sufficient statistics, if I add something more, it will remain sufficient. But whether the completeness is there or it is lost, that is my question. Sriram. Spandan Haldar. Anushka. Priyanshi. So if you consider, say, a function of this as x bar minus s square, then expectation of gt is equal to expectation of x bar minus s square. In the Poisson distribution, the mean and the variance both are lambda. So expectation x bar is lambda, expectation of s square is also lambda. Because the sample mean and the sample variance are unbiased estimators of the population mean and the population variance. Actually, I should say that it is not 1 because this is a discrete distribution. So T is incomplete. Okay, let me give one more problem here. I am considering random sample from normal theta square. Okay. Okay, so find the minimal sufficient statistic. And check if it is complete. So please solve this problem. Yeah. So anybody has come up with the minimal sufficient statistics? What is the minimal sufficient statistics here?
Same as mu.
Sigma xi comma sigma xi square
X
or
bar.
x square.
Okay, so sigma xi square, sigma xi square, or we can write say t star, that is x bar s square. Okay, so this is minimal sufficient. Now my second question, please answer whether it is complete. So is it complete? Jay Kumar.
Sir, I am trying, sir.
Okay. Likhit Reddy.
Strings.
Okay. Please try and tell me.
Sir,
Yes. Yes.
sir, haven't we solved the same question earlier?
So what was the answer?
Sir, in that case, T was not sufficient.
Not.
I mean, it was not complete. Not complete.
Okay. What is the statistic? What is the statistic which is used as counter example?
Sir,
What is the
X
statistic?
bar minus S square.
No, that is Poisson distribution. This is normal.
Okay.
You are confusing
okay,
with the
sir.
Poisson distribution.
Okay, sir.
In the Poisson distribution, mean and variance are same. So expectation x bar was lambda and expectation s square was lambda. But here expectation of x bar is theta and expectation of s square is theta square. So expectation of x bar minus s square is not 0. So your statement will not hold here. You have to check separately. I mean, something else has to be tried. Either it is complete or not complete. If it is not complete, then you have to get a similar function.
Sir?
Yes.
So in the previous question, the expectation of s square is n by n minus 1 lambda, right?
Here, no, s square is 1 by n minus 1 sigma xi minus x bar square. That is unbiased for the population variance that we have shown earlier in general. So this is unbiased for lambda. This is also unbiased for lambda. So it is okay.
Yes, sir. Since it is an unbiased statistic
So
estimated for variance, so we make it lambda.
yeah. Because in Poisson distribution, variance is lambda, no?
Yes, sir. Yes, sir.
But here I am taking different thing. Here mean is theta, variance is theta square. So the same statistic will not work if at all. Something else has to be tried. So let us look at the distribution. Okay. See, the purpose of doing a lot of distribution theory is that, so distribution of x bar is normal theta, theta square by n. So if I consider expectation of x bar square, then that is theta square plus theta square by n, that is n plus 1 by n theta square. Okay. So this means that n by n plus 1 x bar square, expectation of this is equal to theta square. Also expectation of s square is theta square. So if I consider the function gt is equal to n by n plus 1 x bar square minus s square, then expectation
Sir?
of gt, yes. Yes.
Sir, how you get the statement like expectation of x bar square is n plus 1
What is
by
the
n
second
theta
moment
square?
of what is the second moment? What is the definition of the second moment? What is the definition of variance of a distribution? It is mu2 prime minus mu1 prime square.
Yes, sir.
So mu2 prime is mu1 prime square plus variance.
Okay, yes, sir. Yes, sir. I got it.
Theta square plus theta square by n.
Okay, sir.
But probability that gt is equal to 0 is not 1, because this term, why should they be equal? So t is incomplete. So here also the minimal sufficient statistics is incomplete. Now the next results which I will be giving, it will be clear that why this kind of study is important actually. Why should we study such things? This completeness property, what does it lead to? So let me firstly consider another variation also of this completeness. So there is a little bit of, you can say, relaxation of this completeness. It is called boundedly complete. Okay. Another thing which you must be interested in, that here actually I am trying to see whether the minimal sufficient statistics is complete or not. But suppose I am not having sufficiency concept, suppose I don't understand that thing, and I look at the completeness independently. So what should be a complete statistic? Which statistics I should try to prove that it is complete in a given problem? Okay. Fortunately for the exponential family of distributions, we have a nice result actually. So I will state the result without proof here. So under certain conditions, the form of complete statistic can be derived. So we have the following theorem. So exponential family I have already explained to you. Let me write the general form here. So we have a k parameter exponential family. This I have introduced earlier when I was doing this concept of lower bounds. There I have actually, if you apply the factorization theorem, we have seen that here T1, T2, Tk will be a sufficient statistics if the parameters theta 1, theta 2, theta k are linearly independent. That we have seen here. So if I consider this statistic T as T1, T2, Tk, then this is complete provided the parameter space is k dimensional. So to write it in a more mathematical terminology, we write it contains k dimensional. Basically, open sets are closed sets, so we can just say k dimensional cells. So I can write k dimensional rectangles basically. So whatever results we have done, please check all of them. Okay, that I am leaving as an exercise for you. Our next result is actually an application of this concept of sufficiency and completeness. Earlier we have done Rao-Blackwell theorem. Now we add here Lehman-Shafi here. So I am just calling it Rao-Blackwell-Lehman-Shafi theorem. Okay, basically completeness part was discovered by these people, and Rao-Blackwell, they have used the sufficiency, and I had given you the earlier result that given any unbiased estimator, you can actually consider a better unbiased estimator by conditioning on the sufficient statistics. What Lehman-Shafi did, that they actually implemented completeness on that. And if completeness is also there for the sufficient statistics, you actually get the UMVUE, that is the uniformly minimum variance unbiased estimators. So this is a very, very powerful result. So let X have maybe I should write it in a proper form. Let X1, X2, Xn be a random sample. Okay, with some parameter theta. So here I am writing, say, X is equal to X1, X2, Xn, and theta is some parameter which may have more than one dimension. That means every function of the complete sufficient statistics is uniformly minimum variance unbiased estimator of its own expectation. So this is actually a very powerful result because it says that in any given estimation problem, if we want to simply find out UMV then all that we need to do is to just consider a complete sufficient statistics and any function of that such that it will be unbiased for the parameter for which I am looking at the estimator, and then it will become simply the UMV. That's all. So the complicated method of the Rao-Blackwell lower bounds or other lower bounds, etc., are not required. Chronologically, if you see the result of lower bound, they were proved in 1945, 47, etc., and this came in 1950s, 55 basically. So therefore, chronologically, the development is in the same order. Let me firstly prove this one. Proof is of course not very difficult. So let us consider, say, dx so suppose I am considering unbiased estimation of a parametric function, say g theta. Okay. So let us consider, say, d star t, that is expectation of dx given t is equal to t. So we have already seen that since t is a sufficient statistics, the conditional distribution of x given t is free from theta. So this term will be free from theta. So by Rao-Blackwell theorem, we have seen that d star t is unbiased for g theta, and variance of d star t is always less than or equal to variance of dt. Sorry, dx. So now let us consider ht, the function which is with which we started with this function ht. So expectation of ht minus d star t, that is 0 because expectation ht is g theta and expectation of d star t is g theta. So for all theta, this is expectation is 0. And this is a function of complete statistic because t is complete. Since t is complete, it implies that probability that ht is equal to d star t is equal to 1 for all theta. So d star and ht are the same. So ht is UMV. of g theta. So this greatly simplifies the problem of minimum variance unbiased estimation. In a given problem, the first task should be to determine a complete sufficient statistics. If that is available, then for a parametric function, we have to construct an estimator which is based on the complete sufficient statistics and which is unbiased for that parameter. So by Rao-Blackwell-Lehmann-Schaffe theorem, it will automatically become uniformly minimum variance unbiased estimator. So is the theorem clear, the statement and the proof?
Yes.
First of all, let us see for many problems we had shown using the Rao-Kramer lower bound, the result came for the minimum variance unbiased estimation. But one drawback of the Rao-Kramer lower bound was that if for a parameter theta I am able to obtain a UMV UE by constructing that the variance of the unbiased estimator is equal to the lower bound, then for any non-linear function of that parameter, we cannot apply Rao-Kramer lower bound because it will not be attained. We have shown that for parameter, if it is attained, then other parameters for which it will be attained will be only linear functions of that. For non-linear functions, it will not be. So now let us see, because unbiased estimation problem or estimation problem for other parameters is an important problem, because it is not necessary that only for one parameter we will solve the problem. In a given statistical inference situation, there can be so many type of parametric functions for which you need the unbiased estimators. So this will give you, so let me start with something simple and then we will move to complicated examples. Okay. So I am always generally starting with the Poisson distribution or exponential distribution, etc., because here the mathematics is nice. So here T is equal to sigma xi, that follows Poisson and lambda, and this is T is complete and sufficient, that we have shown. So of course for lambda we have x bar, okay. This we have shown using RCLB also. But suppose I am taking g lambda to be lambda square, okay. I am just changing my problem. Can you tell me the answer here? Can you construct an unbiased estimator based on T, which will be UMVUE for lambda square? So I'm just asking you now because the distribution theory I have written here itself. So you can just see. Is the problem clear?
Yes, sir.
Yeah. So please try and tell me. Yes, could you get the UMVUE?
Sir, 1 by n square into t square minus t
1 by n square,
into t square minus t.
this one.
Yes, sir.
Okay, so let us look at the proof of this. See here in the Poisson distribution, expectation of t square. What is the second moment of a Poisson lambda? It is lambda square plus lambda. So it will become n square lambda square plus n lambda. So this is equal to n square lambda square plus expectation of t. So this we bring to the left hand side. So t square minus t by n square. So expectation of this, it will become lambda square. So this is a function of complete sufficient statistics. So we get that 1 by n square t into t minus 1. This is UMVUE of lambda square. Okay, so let us move to another problem. Suppose I take x1, x2, xn following normal mu1. Okay. And I am considering the function g mu is equal to mu square. So please answer this question also.
T square minus 1 by n square.
What did you say? Just repeat it.
T square minus 1 by n square.
What is t?
Sigma xi.
Sigma xi. So what did you say? T square minus
1 by n square.
like this?
Whole divide. T square minus.
Okay, okay, like this. Okay, so let us look at it. See, so here t, if I take say x bar itself, then x bar follows normal mu 1 by n. Okay. Then expectation of x bar square, that becomes mu square plus 1 by n. So if I consider x bar square minus 1 by n, then that is mu square. So this is x bar square minus 1 by n. Let us call it say t star. So this is UMVUE for mu square. Let us look at some other problems also. So x1, x2, xn follows normal mu sigma square. Here both the parameters are unknown. Okay. Actually, for sigma square, we have not been able to apply the Rao-Kramer lower bound. I have shown you using the Rao-Kramer lower bound that the bound was not attained. Okay. So here we have to prove it using the completeness and sufficiency. For this problem, let us see. Firstly, let me write down the joint distribution. 1 by root 2 pi to the power n sigma to the power n e to the power minus 1 by 2 sigma square sigma xi minus x bar xi minus mu square. Okay. This we write as 1 by root 2 pi to the power n sigma to the power n e to the power minus n mu square by 2 sigma square, then e to the power n mu x bar by sigma square minus 1 by 2 sigma square sigma xi square. This I will write like this, mu x bar. Okay. This we have done several times actually in the likelihood estimation, in the Neyman Fisher factorization theorem, in the Rao Kramer lower bound. Several times I have written it, so I need not explain it too much here. You look at this, if I consider this parameter as theta 1 and this parameter as theta 2, so I can consider it as theta 1 T1 plus theta 2 T2, where theta 1 is n mu by sigma square, theta 2 is minus 1 by 2 sigma square, T1x is x bar and T2x is sigma xi square. Or nx bar you can put both ways, it is all right. Whether you want to write, suppose I put this as this one, then this is nx bar or sigma xi. Okay. Hello. So if you consider here this as the two parameter exponential family, then here parameter theta 1 is any real and theta 2 is negative number. Okay, because sigma square is positive, so minus 1 by. So the parameter space theta, it is two-dimensional space. Basically, I can write it in the set theoretic form as minus infinity to infinity 0. This contains two-dimensional rectangles. Okay, because it is two-dimensional problem. I mean, if I consider this as theta 1, this as theta 2, then theta 1 is minus infinity to infinity and theta 2 is negative. So it is this part. So definitely it contains two-dimensional rectangles. So T1, T2 is complete. And of course, by factorization theorem, it is sufficient also. Hello. As a consequence, you can also say x bar s square is also complete sufficient because it is a one-to-one function of this. So expectation of x bar is mu, expectation of s square is sigma square. So from here you conclude that s square is UMV UE for sigma square. For mu, we have already proved that x bar is UMV UE. So this is the missing part which was not there, but now we are able to do that. Okay, so this is important here, that this theorem is more powerful than the lower bounds method, because lower bound method is not always producing the UMV UEs. I will give you some more problem here. Suppose we consider a general normal distribution. Okay, so this is mu here. You are all familiar with the 3 sigma limits in normal distribution. All of you understand that 3 sigma limits?
Sir, could you just explain it once here?
See, if I consider a standard normal distribution, okay, then we have seen that probability of -1 less than or equal to z less than or equal to 1, that is approximately 0.68. -2 to 2, that is approximately 0.95, and -3 to 3 is 0.9987. Okay, this one you know or not?
Yes, sir.
Yes, sir.
Okay, so now if I am considering a general normal distribution, that is x follows normal mu sigma square, then z is equal to x minus mu by sigma. This follows normal 0 1. So here if I write x minus mu by sigma, then what are the statements I will get? Mu minus sigma to mu plus sigma, that is approximately 0.68. Mu minus 2 sigma to mu plus 2 sigma, that is approximately 0.95, and mu minus 3 sigma to mu plus 3 sigma, that is approximately 0.9987. Is the statement clear now? So let me put this as mu
Yes.
minus sigma, mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. So what I am trying to just get at, what I'm trying to get at. From the inference point of view, what is important in this particular description? Yeah, from inference point of view, I mean, why these things are important? What we would like to do?
So within one standard deviation of mu, most of the distribution is contained.
No, that is all right. But what we would like to do? That is all right. What you said is fine. So what we would like to do now? I mean, what is the problem? From inference point of view, what is important now? What we would like to
for
do?
the estimation of mu and sigma.
No, estimation of mu and sigma is already done. So we would like to find out estimates of mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, etc. Or in general, I can say I want to find out estimate of mu plus p sigma, isn't it? Something like that. So suppose I put here condition something like this: probability of x less than or equal to, say, some number I will write, okay, q, that is equal to p. In the standard normal distribution, so in the general normal distribution, if q is the point such that the probability up to this is p, so these are such points, isn't it? Because mu minus sigma to mu plus sigma, it is 0.68, mu minus 2 sigma 2. So these kind of points are important. We would like to estimate such cutoff points, isn't it? In a given problem, we would like to find out these cutoffs. So in general, if I say q is a cutoff such that the probability p is attained, then what does it represent? Okay, so let me just see. Let us look at interpretation of this. The cumulative distribution function of a standard normal, that is denoted by phi function. So basically we can say q minus mu by sigma is equal to phi inverse of p. Phi inverse of p, I can use some other notation. Suppose I use a notation alpha. Okay. So basically then this q point is mu plus alpha sigma. So mu minus sigma, mu plus sigma, mu minus 2 sigma, mu plus 3 sigma, they are all part of such problem where alpha can take different values. In particular, I have taken such value where if I write alpha is equal to phi inverse p, this q, so I'll write it as qp, is the pth quantile of normal mu sigma square distribution if alpha is equal to phi inverse of p. So apart from estimation of the mean, I am writing down a more general estimation problem. For alpha is equal to 0, this will become equal to mu. For alpha is equal to 1, minus 1, 2, minus 2, 3 minus t, etc. So different problems are arising. So in